Hey guys, I don't see anybody, but I see there are people here. Oh, there's Jack, Maya, Matthew. Awesome. Hey, did I beat Catherine? I beat Catherine. There she is. I beat her for once.
Hi, everybody.
How are you all holding out?
Pretty okay.
Yeah. Maya, Jack, you guys okay?
Yeah.
I'm preparing a very late lunch.
From all the college now.
Yeah, Jack, is Pomona very quiet?
Not really, because we're all in the same dorm right now. We're all in Oldenburg, this one building.
They combined you into the same dorm?
Yeah.
So who do we have? We only have 4 right now, so we'll give it a couple of minutes.
I desperately need Kaylee to join because Kaylee is like the world expert on delightful like iPad drawing apps. And I have this tablet that I bought like in a buying panic frenzy like 6 months ago and haven't used very much. And I'm like, I really think that there's going to be some delightful way for me to make like color-coded fun notes. So we're going analog today, but
yeah,
I'm looking forward to doing a deep dive of like tablet-y things.
Yeah, I'm planning to use mine a lot. So most of today, I think we're gonna be on here. So I'll just share my screen, and it's cool that you can share the iPad screen in a Zoom presentation. So then I can write on it, and
yeah, totally.
that'll all work.
Prof. Bachman, could you post the slides like before the lecture each day?
Yeah, so I just posted them. So they're up now. So if you go to the Piazza page, if you go to the resources page on Piazza, then you'll see there's actually the last set of slides never got posted. So there's I think I posted 8AB, which is discrete surfaces. That's what we did last time. And then just 5 minutes ago, I posted 9A, which is discrete curvature integral. So you might want to pull that up and have it on. If you got 2 monitors up, it might be nice to have that on one monitor and have me on the other monitor, or just be able to look at it later. Look at the whole class. Everybody's joining us. It's so nice to see everybody again.
Hi.
We got 7 now. Maybe let's give it another 2-3 minutes and see if we can get a few more. So on that resources page on Piazza, there's a category for the lecture slides. And so I'll keep putting those slides up, the PDFs there. And then we'll put a new category up for lecture videos, because I'm going to record each class and we'll put links to those recordings. And then I'll make a private YouTube channel, and we'll put links to each of those YouTube videos on Piazza as well under the resources tab. So if you miss class, or if I lose you, or you fall asleep in the middle of me talking, then you can go back and rewatch that. We all here? Look at that. Several people just joined us at once. Hi, Kaylee. 1, 2, 3.
Kaylee, get ready to get interviewed about various tablet drawing programs later.
Oh my goodness. I will give you all of my expertise.
Also, you should know that you featured in an anxiety dream I had last night.
Really? Oh no! I think I
I
actually had an anxiety dream about you, like right before spring break. What was the dream?
In this one, I was administering an exam to a very large class, but the class was split into like multiple rooms that were like really far away. So I was like running between the rooms trying to like help people with their exams, and like you had like a totally reasonable question, but I couldn't, like I hadn't written the test or something, so then I didn't know the answer, and I could tell that you could tell that I didn't know what was going on. It was like, Yeah, if you
That's
teach
very
long enough,
stressful.
eventually you start getting like test-related stuff, but from the teacher's like anxiety dreams, but it's not about like you forgot to study for the test. It's like you forgot to prepare for the test. And then, yeah, it was very
That's
funny.
hilarious.
I woke
I'm
up
very
and I was
sorry.
like, at least it was like a nice student that I enjoy. You know, I was like, okay, it was could have been worse.
Kaylee would have been fine with it, I'm sure.
I was like, Kaylee would, even my subconscious while I was unconscious was like, you know, Kaylee would be really understanding about the situation.
That's good. That's good.
Look at our turnout. Great job,
I know.
everybody.
This is
That's
awesome.
so cute.
So good. All right, this might be as many as we're going to get. What do we have? 4, 5, 6, 7, 8. We've got 8. Is that right? No,
We're in the Brady Bunch, everybody.
it's very Brady Bunch.
I know, we got 12. We got everybody.
Oh, awesome. We're all here. That's shocking. That is shockingly good.
Incredible.
Yeah.
By shocked, we mean delightful.
Yeah, that's delightfully good. That's shockingly delightful. Couple of quick announcements. I hope everybody saw. I mean, I'm assuming you're seeing my Sakai emails since you're all here and you got the link to this class. Other things I mentioned, I had to switch my office hours. So instead of Tuesday, Thursday, they're Monday, Wednesday now. And they're a half an hour earlier as well. So they're 9 to 10:30 Monday, Wednesday, if you need my help. I don't know, Catherine, I don't know if you're keeping your office hours the same.
Yeah, actually, I could use some feedback from the class. Actually, since everybody's here, you feel free to use the chat window to like let me know if there's other times that would work well for you. I know we have a lot of seniors in the class who are also doing clinic, and if your clinic teams are anything like the ones that I'm supervising, we've had a little bit of churn on our meeting times. So if my current office hours, which are 3:30 Tuesday and 2:30 Thursday, don't work for you, or if there's some other time that would be better, like we could do an early evening or like by appointment, I'm totally open to your suggestions. We want to make sure that like we're available when is a good time for you to be working. So I set the Zoom meeting links for this week just as they have been. But if there's other times that are better for you, I'm more than happy to like move things around. So yeah, just let me know like what it might, yeah, it might be better to kind of check back in a couple of days when the dust is kind of settled from the changes. But yeah. The other thing that we wanted to talk about a little bit is the grading options for the class. This is a little bit inside baseball, but I know we have students from a couple of different campuses, and the different campuses have been having the same discussion that Harvey Mudd has about whether or not it's appropriate to have a blanket policy that we're just going to move to pass no credit for all classes, or if it's better to just say business as usual, we're going to stay on grades. And it's something that your professors are thinking a lot about. And Dave and I talked, and we decided that for this particular class, we're going to go credit, no credit. And if for whatever reason you have circumstances such that a letter grade is more appropriate for your personal situation, we're happy to hear your argument as to why that is. But we think just given the upheaval in your schedules and days, we just want you to get as much out of the class as you can. There's really no reason not to go past no credit unless there's some other circumstances that you're in. So we felt that a default for this class should be pass no credit. Is that fair?
Yeah, you should all be aware that we've been talking to people at other colleges too. Like some students are worried medical schools typically only accept letter graded classes, but it looks like almost every other college is going to be making exceptions for spring 2020 classes. Everyone in the country and everyone in the world knows this is going to be a weird semester.
And even for things like medical school or vet school are the only ones that I can really think of off the top of my head where they're less understanding about deviations from letter grades, I can't imagine that people downstream looking at the semester are gonna have the same outlook. So
Yeah.
I feel like all of you, I mean, I thought about everybody in the class individually, and I really think for every single one of you, having a pass versus a letter grade for this semester should be totally fine, at least for this particular class.
Yep. Couple of things during class. I'm gonna try to just do this live like this, like we're about to do, but my schedule is still in flux because I have to coordinate things with my family who's also all home. So I may in the future start to pre-record some of these lectures and just post links. So I don't know how long we'll do this like this, but I'm hoping I could keep doing this because I think it's better to do it live. That way I can answer questions as they come up. I like seeing all your faces. So even when I start sharing my screen, I don't know if everybody's going to see everybody else, but I've got 2 screens up. So I'll be able to continue seeing your faces as well as being able to share my screen. And that visual feedback is nice. If your camera is broken or you just don't want to share your video, I understand. I mean, you don't have to, but it's nice for me when I'm talking to see your expressions and see if I'm losing people. And the other thing is, yeah, I like the, Garrett, I like the little thumbs up. That was good. But the other thing to make use of, you can always turn your mic off and just interrupt me and ask a question, or you can use the chat window. I've got 2 monitors up. So on my other monitor, I've got the chat window. So as people ask questions, I'll glance over occasionally and see if there are questions, and I'll try to answer them as soon as I see them.
Yeah, and also if you feel like typing a little, you know, even if it's just a thumbs up or a happy face or whatever you want to type in the chat window, like I'm happy to be all of your voices. So if you feel like muting yourself for whatever reason and you just want to like get our attention, like I'll be monitoring the chat window as well, and I can kind of like pipe up, like, oh, you know, Morgan has a question or whatever. So
We good? We ready to jump back into it? Okay, I spent a lot of time looking at the next couple of lectures. Thanks, Riley. Frankly, the next 4 lectures that Keenan had posted are a little bit of a mess. I'm starting to get the impression that the later lectures that he has up, maybe he never got to those when he did the class himself, because I'm sure he wouldn't have done things this way. So I've had to rewrite the next 2 lectures. I've split up into 3 lectures, and some of that is going to affect the assignment. So I sent some lengthy emails through Sakai, and I'm hoping you all got those. We're going to talk about material related to specific homework problems on assignment 4 in each of the next 3 lectures. And they're kind of out of order. Like today, we might talk about some of the later ones in assignment 4. Next time, we're going to talk about some of those middle ones in assignment 4. They're kind of all mixed up. And you'll find some of the answers to some of the problems in assignment 4 are embedded in these lectures. I'm not going to point it out so explicitly, but if you pay attention, you'll see some answers to some homework problems as we go through.
Dave, isn't it nice to know that even NSF Career Award, Young Career Award recipients' classes fall apart after the first half because they run out of time, and then they just put it in like conference talks?
Yeah, so this just happened. Keenan Crane was just awarded an NSF Career Award, which is for people, I think it's 5 years or 7 years out of their PhD. There's some window. You have to be young enough or recent enough PhD.
The cusp of getting tenure. It's like, I guess not at CMU, but it's usually like new-ish faculty that have started to graduate a few PhD students but aren't like tenured and crotchety yet.
Yeah, I think you have to be in a tenure track position, but not yet tenured and within 7 years of your PhD or something like that. It's a big deal. He's kind of a hotshot. All right, so without further ado, I'm just going to jump into it. I hope you all are set on your due dates. Let us know if there are questions about the due dates. We're going to keep the coding assignment due on Thursday because you don't really need to know anything to do the coding assignment besides what's in the coding assignment.
That's pretty standalone.
Yeah. Let's see. I'm trying to share my screen now. Give me a minute.
Oops.
All right, does everybody see that slide? Just give me a nod or a thumbs up or, yep. All right, awesome, cool. All right, so we'll just go through it, and I'll mention there was a bit of a mix-up in notation. I did say this over over Sakai. Wait, hold on one second. Let me just change things a little. I got to just change how my monitors are set up. I want the class on one window so I can see you guys. Just give me 1 second here. Okay, sorry. All right, I'm all set up now. All right. Now it says my screen sharing is paused. What just happened? Okay, better. You all see that now, right? It says discrete curvature integral. Good, cool. All right, let's get started. All right. Last time we saw all these different, over the last couple of classes, we saw all these different concepts of what we mean by curvature in general. So in the smooth theory, we had Gaussian curvature, mean curvature, and principal curvatures, and sectional curvatures in different directions. There were all these different things. They all related to the shape operator, and there's a lot of technical stuff. So some of that we're going to use, some of it we won't use. You won't see the shape operator, but you'll see all these curvatures appear. And the strategy is going to be the same, the strategy we used when we did things like differential forms, where if you want to define the value of a differential form at a point, you just integrate it around the simplices around that point, and that total integral that you get is the value you assign to that point. So that's kind of the strategy for all these curvatures, is generally we're going to integrate smooth curvature over all the simplices around a vertex to get the value at that vertex. That's one strategy. There's a couple of different strategies to discretize curvature that we'll see, but that's a common one. Okay, so we already saw all these ideas, and why isn't my slide changing? What just happened? Are you all still seeing the bunnies? Okay, I'm advancing the slide, but it's not advancing. All right, I'm having technical trouble.
It did change
How about now?
briefly.
There we
Yeah.
go. All right, better. Okay. Again, just to remind you, I mean, these were the smooth pictures. There's the shape operator. We will briefly use the principal directions. So what you're seeing, or I could use my pencil here. What you're seeing here and here, the normal directions and the two principal directions, x1 and x2. Remember, those are the directions of maximal and minimal principal. Those are the principal curvatures. So maximal and minimal sectional curvature. So if I'm standing on the surface and I look this way, I'll see the most curvature one way. And then as I turn, the curvature changes. And then in the other principal direction, I see the least curvature, either going up or going down. And those directions always end up being orthogonal, which is an interesting fact, not something we're going to use so much now, but an interesting fact to remember. To discretize things, we'll use a lot of the stuff that we did. We're going to introduce some new stuff like Steiner polynomials we'll do later. We're going to look at some variations. So variation, there's a whole subject. You could take a whole semester class on a subject called the calculus of variations, where you look at how functions vary along other functions and how that affects their values. And you can base a lot of invariance that way. So we're going to do a tiny bit of that in 2 classes. That's the 3rd lecture. I don't know why he had the Laplacian on there. That's that 3rd thing. It's Gauss-Bonnet, Schlafly. We'll see a particular formula called the Schlafly family. We won't use the Laplacian at all over the next 3 lectures. And this is what we're headed toward. So this is the big picture. We're going to keep coming back to this picture over and over and over and over and over again. Okay. This is on the left-hand side of the picture. Those are all the smooth invariants that we're going to look at, and we're going to try to discretize. So going from the top to the bottom, The most basic kind of thing you can say is if I have a closed surface, what's the volume that that encloses? That's the one on the top left, the volume of M. And then going down from that, we can look at how to discretize the normal vector times a little area element. So that's one way to scale the normal, is to multiply by a little bit of area. And then you can, of course, integrate the area element over the whole surface. The integral of dA over the whole surface M, that's just the area of M. So he wrote that as an integral just so you can see that relation between the second and third thing there on the left-hand side. But the integral of dA, you should just think of as the area of the surface. And then in the third lecture, we'll see how the variation of that gives you the mean curvature times a normal vector times a little area element. So that's that HN dA. I should be marking these as I'm talking about it, right? So this right here is area. This right here is mean curvature times normal. You're not seeing that. Why are you not seeing that? I'm circling things and you're not seeing it, are you? No. Shit.
You can draw over the screen directly in.
That's what I'm doing. Yeah. Here's my. Can you see me at all in the camera view? Here's my iPad screen, and things are circled on my iPad screen, but they're not being circled on the sharing screen. Well, I'll have to just work that out. We'll deal with it for now. That's weird. Tell you what, let's stop this. I'm gonna just try one more thing. I'm gonna stop my screen share just for a minute. And we're gonna do things a little bit differently. Give me a minute, I gotta set it up differently. I don't know what you're seeing right now. Let's see. Start share. All right, hopefully you're seeing the bunnies again. And now.
I can see a whole window that looks like your preview window with the sidebar, the thumbnails.
Yeah. Now you're seeing, oh shoot. Now you're seeing two different slides, aren't you?
Now I can see just the single page of the bunnies.
Same here.
Is it filling up the screen?
Yeah, it's the whole screen.
Yeah, it's just the bunny slides.
Would it be helpful if one of us shared our screen with you, Professor?
Maybe. Just give me a second here. I can't get this in full screen and present it at the same time. That's the problem.
Did anybody have a little thing show up that was something about the presenter's cursor? I had something pop up that said something about being able to see the, oh, now I can see your cursor.
Yeah. So the only problem now is that this slideshow is covering both my monitors, so I can't see like the chat window or any of you guys, which I don't like. So I can either like present on my computer and then I'm seeing you guys, or I can present on my iPad. I think that I'm just going to present from my iPad and not worry about making notes on it for the moment. We'll have to work that out. So let me just go back to how I had it. Working out technical difficulties here. So, share play. All right, Better, you're at least seeing my iPad screen, right? But nothing's circled, that's fine. All right. Anyway, just if it's not so important. If we go down, as we go, I'll explain each of these things. The left-hand side is the smooth theory. I think it's fairly self-explanatory if you just remember what the letters are. H is mean curvature, K is Gaussian curvature, N is normal vector, dA is an area element. So everything there on the left-hand side down the smooth column should be pretty self-explanatory. The stuff that's new is the middle column. That's the most important stuff. That's the discretization of all of that smooth stuff. And I've outlined there in the giant red rectangle. In the giant red rectangle, I've outlined everything we're going to talk about today. So all the red arrows going from left to right, we're going to explain each of those arrows today. And all those formulas in the center are the formulas that you're implementing in your homework. So you're coding a homework assignment. You don't have to understand where those formulas come from. You're just going to code up those formulas. You don't have to know anything about what they mean, but hopefully over the next 3 lectures, you'll understand what they mean and where they're coming from, okay? So the very first one is the easiest one, but before we get to that, God damn it. Sorry, again, I just advanced the slide. Now that I reoriented things, I can't see. No, you guys are still seeing the same thing, right? And I'm seeing something different. What the heck is going on? I should never have messed with it.
Probably half the Zoom users in the world right now are doing the exact same thing.
Yep. I've lost my Zoom window entirely. Let's see.
That looks more promising to me.
No, except it's, oh, hey, there it goes. Okay, better. All right. Hopefully those are the last things. I still can't use my pen and write on the slide, but well, I'm not just going to deal with that today. All right. These are the letters. This is the key to, so you understand all those discrete formulas. So you understand every one of those formulas. These are all the letters you need to know. So I hope they're labeled enough. Does anybody have any questions on what any of these mean? You could just chat it or something. The thing that you have to watch out for is in your coding homework assignment, he switched theta and phi from this slide. So theta in your coding homework assignment refers to the angle between 2 faces of the triangle, and phi in your homework assignment refers to the tip angle at each face. And you can tell from the subscripting, when he wrote out the homework assignment, he's got phi with a little I and a JK superscript. And here he's got theta with a subscript of an I and a JK superscript. So unfortunately, the homework assignment, if you're trying to understand what's going on there and then you look at this slide, you'll get confused unless you're just aware of that, okay? And the other thing is, just going back to this slide, he did the same thing on this. Oh, damn it, why isn't it? What if there's just a timeline? I changed the slide and now you can't see the changed slide. Ah. All right, I'm just gonna give up on my iPad entirely. I'm just gonna do this from my computer. So give me 1 more minute and then I'm sure we won't have any problems. I just won't be able to use my iPad, but that's fine. Still not using the pen. So, sorry, technical troubles again.
Everybody's doing great. We're all here and feeling patient. It's all good. We're going to be such experts.
Yeah. How's that look? You seeing the slide kind of take up the full window there? And now, now how do I advance the next slide? Great. Let's see. All right, well, we'll just live with the little thumb thing on the side. That's fine. Where were we? All right, these are the conventions. Here's where we're at. The very first arrow to explain is the easiest arrow. That top arrow right there is just the volume. And the discrete version is just add up the volume of all the three simplices. Honestly, this one confused me for a while because the V0ijk that's there. Hey, do you see my mouse cursor? You do? Awesome. At least I have that much. At least I have a pointer. So that V0ijk, I didn't understand what the zero was. The zero, and it took me forever to figure out, oh, that's the origin. 0ijk, he's referring to a three simplex. Remember, a three simplex, that's a tetrahedron. A tetrahedron has 4 vertices. One of those is at 0, is at the origin. And then I, j, and k are at 3 vertices on the surface. So you've got this triangulated surface. You've got the triangle IJK on the surface. And then you've got the origin at 0. And 0ijk is a 3 simplex. So we're doing the volume of that. But then we're adding up all of the 3 simplices. So the thing he's summing over are all the triangles. And each triangle is a face, which is why it says ijk element of f on this underneath the summation sign. Right? So ijk refers to a single triangle, which is a single element of f. So if we sum up over all the elements of f, we're summing up the volume of all those 3 simplices. Is that clear? Yeah. Okay. Good. All right.
Question.
What's that, Jack?
So in this way, does the total volume is influenced by where the origin is?
Yes and no. So it turns out it doesn't matter where the origin is. Even if you put the origin outside the surface, you count that as negative volume. And some of that's going to cancel with the positive stuff inside. Really wish I could draw this on my iPad.
Oh.
Right?
Okay. Yeah. I think there's a little part about calculating the area of the thing, like their negative areas.
Yep.
I think I can relate it in the book. Yeah. Cool.
Yep. Okay. The next easiest arrow is just the total area. That one's even easier, right? If you want the total area of the smooth surface, you integrate dA. If you want the total area of the discrete surface, the triangulated surface, you just add up the areas of all the triangles. That's it. Okay. Questions about that? No? Good. All right. Now we're going to move on to the discrete Gaussian curvature. So what I'm trying to do as I'm going to keep coming back to this slide where you see this giant flowchart. The whole point of the next 3 days is to explain every single arrow in this slide. Every time we explain an arrow, it's going to turn green. So you see there are now 2 green arrows in this picture, the discrete version of the area and the discrete version of the volume. But then down on the bottom, you see the next one we're going to talk about is this red one down on the bottom, where we're going to discretize not the Gaussian curvature, but the total Gaussian curvature. We want to discretize the integral of the Gaussian curvature. That's what we're about to do. Okay, so to do that, I got to first remind you of something we talked about pretty early on in this class, which was the Euler characteristic. Is this slide going off the edge of the screen? It kind of looks like it. Let's see, I can shrink it. That's better. Okay. Is it still, you still seeing that slide? Okay. The Euler characteristic is something we saw earlier in the course. You just take the number of vertices, subtract the number of edges, and add up the number of faces. And the amazing thing about the Euler characteristic is it turns out to be completely, it's called a homeomorphism invariant. If you take the same surface, you triangulate it in different ways, you get the same exact Euler characteristic. And in fact, all it depends on is the number of holes in the surface. So if you think of a donut as having a single hole where you can stick your arm through, that's that one in the middle there, that's a torus, right? So here's a nice smooth triangulation of a torus, a nice round torus, or you could have kind of a squared off version of the torus. Either way you do it, you have one hole, and so that's called the it's called the genus, is the number of holes. So G is 1 in that case. Any version of a sphere all the way on the left has no holes, so that's genus 0. On the far right, you see it looks like two tori stuck together and squared off. So that's genus 2. And another way to compute the Euler characteristic is that formula on the top of the screen there. Whoa, didn't mean to do that. Is 2 minus 2 times the genus. So if you think about a sphere, any triangulation of a sphere has genus 0. So 2 minus 2 times the genus gives you 2 minus 0. So that just gives you 2. So any triangulation of a sphere gives you 2. For genus 1, 2 minus 2g ends up being 0. So any triangulation of a torus gives you Euler characteristic 0. And any triangulation of a double torus gives you Euler characteristic minus 2. And every time you add a hole, it decreases the Euler characteristic by 2. So it keeps going down by 2 each time. All right, now we're going to relate the Euler characteristic to some angle stuff. The angle defect at a vertex, you just add up all of the the summation here is a little bit funny. So he's got this capital omega I there, and that is this 2 pi minus the sum of all of those tip angles at vertex I. Okay, so you take all those tip angles going around vertex I, add them up, and if that were flat, if all those triangles fit together and filled up a plane, then the total angle around that would be 2 pi. So 2 pi minus that would be 0. So angle defect is really measuring the deviation from being planar, from being flat. If it's flat, you get 0. If it's more of a cone, you'd get a positive angle defect. If it's more like a saddle, so as you go around, you kind of go up and down around that vertex, you can get a negative angle defect. You can have a total angle sum that's bigger than 2 pi. So that angle defect can be positive, negative, or 0. We can relate that angle defect to some geometry here. If you imagine taking that those triangles around vertex I and kind of puffing them out so that they lie on a sphere, that's really the smooth picture of the Gauss map. If you remember the Gauss map, what we did was we took the normal vectors at every point on the surface. Each normal vector at a point on a surface is just a vector of length 1, and if we place that vector of length 1 at the origin, then it's pointing to a place on the sphere. Catherine, your mic's off. Looks like you're saying something, but your mic's off.
Oh, there we go. So there was a question about the angle defect slide. So I think the question is about, so we have these tip angles that go around a particular vertex. So we have a triangulation, got some triangles adjacent to a particular vertex. You add up the 2D angles of the, I don't know, the corners of those triangles that abut the particular vertex. And looking at that sum, you can tell whether or not that tip is, on a plane with its triangle neighbors, if it's a concavity or if it's a convexity by looking at the sum of those angles. Is that right?
Yeah, Kaylee, I see you asked what the tip angle is. It's just the angle in that picture there. So around every vertex, there's a bunch of triangles coming into that vertex. And each one of those triangles just has a little interior angle at that vertex. And we're just adding up all those interior angles.
So like on this slide, theta I j k would be a single tip angle.
So each vertex would have multiple tip angles?
Yeah, and what we're looking at is the sum of those tip angles. Yeah.
Okay, cool. Thank
So
you.
yeah, so for this, the angle defect for this picture, you're going to do theta ijk plus theta I lj plus the next one around, add all those up, and then when you compute that sum, then you subtract it from 2 pi to get the angle defect.
Could you say again, when is it going to be a negative number?
It's a little hard to say, but if you imagine triangulating a saddle, then one way to think of it is at a saddle, imagine just a Pringles chip. Imagine making a Pringles chip triangulated. So with the angle right in the center, the vertex right in the center, vertex I is right in the center of that potato chip. And then the edges go around the boundary and they kind of wind up and down and up and down. And you'll end up with area bigger than 2 pi. Are you going to go grab a potato chip?
Yeah, I want that.
Oh, he actually has a can of Pringles chips. That's awesome.
Is it what you mean?
Yeah, perfect. Right. So if you put your vertex I right in the center of that, and the other vertices on the boundary of that thing, and then fill it up with triangles.
Yeah,
You're
so
actually doing it. This is awesome.
if you could imagine like putting that angle and then like putting your finger right at the center of the saddle and then breaking the chip right there, there would be no way to sort of like arrange those broken pieces of chip such that it would be flat.
Okay. Okay. Is it like break into this?
Yeah, so
Yeah,
we broke
perfect.
it right
Exactly right.
there.
Yeah. So now if you were to flatten out all those triangles and add up those tip angles in the center, you'd get a number bigger than 2 pi.
Oh, okay. Okay. That's cool. I'm gonna try this later.
Yeah, I don't know. I always kind of visualize it like, I don't know, if you had like a really stiff kind of rubber sheet or something like that, that like trying to squish it onto, if you were trying to squish it onto like a table or something like that, you would always end up with like a ruffle. Like there would be no way to kind of smooth the whole thing without it having a little extra lump in it. I don't know. Chips are more delicious though.
Interesting. Okay.
All right, let's see, going back to this. So what you're seeing in this picture, the arrows sticking out of each face, those are the normal vectors, right? So if we take each of those normal vectors and put it at the origin in R3, then that vector ends up being pointing at a point on a sphere. So in the picture on the right, you see that sphere, and like this point, you all still see my pointer? So this point here on the sphere is the tip of this arrow over here if you were to move this arrow to the origin. So if I move this arrow to the origin, now it sits inside this sphere, pointing at this point, okay? And as we go around, I'll put all these arrows at the origin. They'll point to these 5 points on the sphere. That point at the center of the cone, the triangulated cone on the left, ends up being at the center on the sphere, okay? But now instead of 5 flat triangles, we have 5 spherical triangles, okay? And all those angles, the phi i's are, and he switched theta and phi again, didn't he? The picture on the right, it looks like theta and phi are switched. Because phi, damn it, I hate it when he does this. Yeah, I think that he switched theta and phi for the picture on the right. The angle between two dotted lines is what happens when you flatten out all these triangles onto a sphere. And the exterior angle up here around the point N, that's the angle between two faces on the flattened cone. So that is the angle, supposed to be the angle phi. So he's got those swapped in the picture on the right. All right, so let's think about what angle defect has to do with that picture. Imagine that we take this dodecahedron, icosahedron, and we puff it out so that all the triangles are on the sphere, which he didn't do. He made a pentagon. So each pentagon here is supposed to be a set of 5 triangles in the upper picture. It's not a great picture, but what happens when you do that is that you end up with 4 pi. This is not a very convincing argument. Oh, so the link is something I didn't say, which is what I should have said. So going back to here, the point about the angle defect is you can relate the angle defect to a geometric quantity. So once I take these 5 normal vectors, put them on the sphere, and I get a pentagon, then the area of that pentagon on the sphere is exactly equal to the angle defect. So that's the relationship there between the Gauss map and the angle defect, is that the angle defect is giving you the area on the Gauss map, okay? So that's all he's saying on this slide here, is once I puff that out, each set of 5 triangles gives you the area of one of the pentagons in the lower picture. Those pentagons cover the sphere, and the sphere has total area 4 pi, a sphere of radius 1. The formula for the area of a sphere is 4 pi r squared. So the total area for a sphere of radius r is just 4 pi. So the total, since the sum of the areas is 4 pi, it means the sum of the angle defects is 4 pi. Okay? And that's a general phenomena for any sphere, it turns out. If you triangulate any sphere and you do this, you always get 4 pi. And if you do it for any torus, you'll always get 0. And if you do it for any 2-hole torus, you'll get negative 4 pi. And that should start to remind you of the Euler characteristic. And in fact, the Euler characteristic and the Gauss map were totally related to each other by the Gauss-Bonnet theorem. So this formula down here on the right, we've seen before. It's saying if I take the Gaussian curvature and I integrate it over the whole surface, I get 2 pi times the Euler characteristic. So here's the link. What we're saying is 2 things. We're saying from the smooth theory, we have Gauss-Bonnet. We have the total Gaussian curvature is 2 pi times the Euler characteristic. And now from the combinatorics, the sum of the angle defects is 2 pi times the Euler characteristic. So if the total Gaussian curvature is 2 pi times the Euler characteristic, and the total angle defect is 2 pi times the Euler characteristic, then it must be that the total angle defect is the discretization of the total Gaussian curvature, because both of those equal 2 pi times the Euler characteristic. Okay? So that's the argument. That's why total angle defect is the appropriate discretization of the integral of Gaussian curvature. And that Gauss-Bonnet theorem is the link between the two, really. Okay? Now that total angle defect, again, is just, the angle defect is just the difference between the sum of the tip angles and 2 pi, which is why you see on the next slide that formula is just, can be written out a little more concretely by replacing that omega I expression with just 2 pi minus the sum of all the tip angles at each vertex. And then you have to sum over all vertices. So there's one more summation in that formula, which is just the sum over all vertices. Questions about that? Okay. So that's a nice problem, by the way. There's lots of proofs for that. Going just back to, whoa, don't look at that. Going back to this slide here, the fact that you can compute the Euler characteristic by adding up the angle defects, there's purely combinatorial proofs of that. You don't have to use the Gauss map. You don't have to use area calculations. You don't have to do any integration. That's a purely combinatorial fact. And that's kind of fun to prove. It's a nice little exercise to prove, is that so here's a way to say it. The sum of the angle defect is the number of vertices minus the number of edges plus the number of faces. You could just prove that directly without any geometry at all, which is kind of neat. All right, going back to this picture. Okay, so that's that red arrow that's on the bottom. Okay, we got a couple more red arrows to take care of today. We're going to try to hit all but one of the horizontal arrows on the left-hand side of this picture today. One of them we'll have to postpone to next time because we'll need Steiner polynomials. All right, to do 3 of those arrows, just going back to this picture, we're going to do 3 of these arrows almost simultaneously by looking at some stuff we did last time before break. So I've got to review some stuff we did last time before break. This is where things got a little bit hairy when we were talking about vector value differential forms. And we looked at wedge products of vector value differential forms and integrals of vector value differential forms. So I'm going to try to walk through the calculations as slowly as I can. You know, and again, just you may need to revisit these slides yourself to just kind of stare at them for a while until you sort of figure things out. But a lot of the calculations are the same as calculations we did for forms earlier in the term that I think most people were starting to get the hang of. The thing to remember is that when we're looking at wedge products of vectors, we really essentially mean twice the cross product. V wedge W, when V and W are vectors, is V cross W minus W cross V. But W cross V we can rewrite as negative V cross W. So we get V cross W minus negative V cross W. And that just gives us 2 times V cross W. So putting that all together, V wedge W is just 2 times V cross W. So I'm just trying to remind you of stuff we did before break. It's a lot to kind of follow verbally. I'd be writing this out on my iPad if I could, but I can't right now. So hopefully the slides, you'll see that in the slides as we go. So what we want to do over the next couple of slides, we're going to try to explain these 3 things. Actually, it's all on the next slide. All 3 of those are going to be explained here. So I'm going to try to walk you through these 3 calculations as much as I can. So first, df, wedge df of x1, x2. So x1 and x2 are the principal directions. Well, that doesn't matter so much for that very first calculation. All you have to know is what I just said a minute ago. What do we mean by evaluating df wedge df is we look at their cross products in each order, but the second cross product, you can flip the order, make the negative into a positive, which is why we just pick up a 2 there on the second line of that first calculation, okay? But df x1 cross df x2, so let me remind you what f is. So first, f is just our parameterization of our surface. df is the map that gives us tangent vectors. And x1 and x2 are our 2 principal directions, which are always perpendicular, right? They're always at right angles. So if I take df of x1, that's the tangent vector in the x1 direction. df of f of x2 is the tangent vector in the x2 direction. Are you guys seeing me? I'm like doing these hand motions to the screen. I don't know if you're seeing that. Yeah, okay, good. So df of x1 is the tangent vector in one direction. df of x2 is the tangent vector in the other direction. They're perpendicular, okay? And so when I take their cross product, I'm getting the area of that little square patch, which is just one little area element, which we can just rename dA. So what you'll see is dA in that slide on the right on the slideshow is that dA, but that's just the magnitude, right? The magnitude of the cross product of two things gives you the area of the parallelogram they span, but it's a vector quantity. It points in the direction of the normal vector. Right? If I take two tangent vectors and cross them, I get a normal vector. So the direction is the direction of the normal vector. That's why the n is popping up. The dA is popping up because I just get a little element of area. And the 2 is popping up just because of the algebra. Good. I think that first calculation is the easiest one to follow. And we did that first calculation the day before break too. So this should be just a little tiny bit of a review. The next two calculations we did not do before break. These are new, and these do require you remember a little tiny bit of the shape operator. So, and how we define the principal directions. So I'll just try to go through them slowly. So again, df wedge dn of x1 wedge comma x2, you just plug in x1 and x2 in one order, and then plug in x2 and x1 in the other order, and you subtract. That's how you evaluate any form. This was true just when we did just real valued forms. If you have omega wedge nu of v comma w, that's omega v wedge nu w minus omega w wedge nu v. Right, you just plug in the two vectors in the opposite order and subtract, okay? But now the wedge product, you have to remember, becomes the cross product in 3 dimensions, right? So two things have happened there. We've plugged in the two vectors in one order and then the opposite order and subtracted, and we've turned the wedge product into the cross product. Going from the second line to the third line, that's where we need to remember what the hell principal directions are and what the shape operator is. The shape operator tells us that dn of x2 is the principal direction. It's the eigenvector of the 2 by 2 matrix dn. If you write dn as a 2 by 2 matrix, then x2 is its eigenvector, which means the relationship between dn of x2 and df of x2, they're going to point in the same direction, but they differ by the eigenvalue in that direction. Right? Just remember from linear algebra, if you plug an eigenvector into a matrix, you get out a vector that points in the same direction times the eigenvalue. Okay? And the eigenvalue is exactly how we define the principal curvature. That's where this kappa 1 is coming out. So dn of x2, since x2 is the eigenvector, we get df of x2 times the eigenvalue, which is kappa 1. Okay, so that's why that kappa 1 is suddenly appearing, the principal curvature in that direction. Okay, and then in the second term of this expression, something similar has happened. dn of x1 turned into df of x1 times the eigenvalue in that direction, which should have been, oh, he's got his kappa 1 and kappa 2 switched. I'm sorry. I see some confusion there. And now I'm realizing he switched things. That should have been a kappa 1 there in the second term, right? dn of x1 is df of x1 times kappa 1. And so that should have been a kappa 1 there. It doesn't matter for the third line. We just get the sum of the two, kappa 1 plus kappa 2. So we should have had a k1 in the first term, a k2 in the, k2 in the first term, k1 in the second term. We still get k1 plus k2 on the last line of that calculation.
The subscripts should just match.
The subscript should just match. Yeah, it should have been k2 plus k1 instead of k1 plus k2. Okay, I should have caught that before today. The sum of the eigenvalues is exactly twice the mean curvature. Remember the mean curvature, the reason why it's called mean curvature, the word mean there is not meaning angry, it's meaning average, right? We use mean in statistics for the word average. The average of the curvature is, well, if I'm just averaging two values, I take their sum and divide by 2, right? So h is k1 plus k2 over 2, which means 2 times h is just k1 plus k2. So that's why we get this 2h over here. The direction is, again, perpendicular to the two tangent vectors. and we pick up, since we're taking the cross product of those two tangent vectors, we pick up a little bit of area element, which is what the dA is representing. So we have a little bit of area times in the normal direction times twice the mean curvature. Okay, if you followed all that, that last part should be easy. So again, we're plugging in x1 and x2. We do that by plugging them in both orders and subtracting. Okay, that's the first line. In the second line, the dn of x1 turned into df of x1 times kappa 1. The dn of x2 turned into df of x2 times kappa 2. All right, that happened in the first term. That also happened in the second term. We can switch the cross product in the second term and change the negative to a positive. So we come up, pick up another factor of 2 there in the third line. And the product of the product of the principal curvatures is exactly how we define the Gaussian curvature. So that's where we're getting the Gaussian curvature now in the very last line. And again, df cross df is turning into nda, just like in the other two calculations. There's a lot going on in this slide. It's worth going back and revisiting yourself and staring at it a while. Make sure you understand all these lines. It's fairly straightforward if you understand all of the algebra that we did before break, which is a big if, right? Remembering wedge products and cross products and what they mean for vector valued forms. I think the good news is that we're going to have to remember very little of that stuff from here on in. A lot of that stuff we're just going to use for this one slide, and that's it.
Question?
Yeah.
So I'm pretty okay with the things on this slide, but like if I say dn wedge dn, then 3x1 plus 2x2 and minus 1x1 plus x2, like not exactly the two very good principal curvature directions.
Yeah, not what
they just don't give me the form like that.
It'll give you something similar. Yeah, it breaks up over sums because everything's linear. Yeah.
Okay.
Yeah, like dn of x1 plus x2 is dn of x1 plus dn of x2, which you can then write as k1 df of x1 plus k2 df of x2. So
okay.
you have to break things up over the summation. Yeah.
Cool, thanks.
Good. Any other questions? All right. So we've got these three formulas now, and now we're going to use each of them in turn to do some calculus. We're going to do some integration. So again, remember this, the strategy to discretize is we integrate around a vertex, and that's how we, the total integral is what we define to be the value at that vertex. So if I want the Gaussian curvature around a vertex, I integrate around the vertex, and then I know what the Gaussian, how I'm going to define the Gaussian curvature at the vertex, okay, which we'll do in a minute. The vector area is something we looked at before break, the integral of not dA, but the normal vector times dA. And just going back to that previous slide, the normal vector times dA is just df wedge df. Okay, so going forward, the normal vector times dA is just df wedge df. There's a factor of 2. It was actually 2 times the normal vector. You can bring that 2 over to this side, and it turns into a 1/2. Okay, and now we're going to use the generalized Stokes theorem. Generalized Stokes theorem says I can replace the integral around omega. Omega is a bit of the surface with the integral around the boundary of omega. If I replace the d, if I remove one of the d's essentially. So the derivative of f cross df is df wedge df. And again, there's some funny stuff with this factor of 2 that you have to think about. So now we can use that, again, to get the normal, to get one type of way to define the normal at the vertex. So if I think about going through this calculation, the stuff that's at the very top of the page there, if I go through this calculation, again, I've got the integral of nda is 1/2. So Why is that 1/3 there? Anybody know why the 1/3's there? The hint is right here. We're only integrating NDA over a dual cell. So if you look down in this picture on the bottom right, the way you integrate over a dual cell is you integrate over all 6 of the cells in this picture, and then you just take 1/3 of that. Because the shaded part of triangle IJP is 1/3 of the total of IJP. So that's why that 1/3 is there, because we're going to integrate actually over all 6 of those triangles, but then take 1/3 of it to just get the integral over the dual cell. Okay? The 1/3 turns into a 1/6 because of the 1/2 at the top of the screen. Okay? So we got a 1/3 because we're looking at the dual cell. That turned into a 1/6 because we picked up a factor of 1/2. The NDA turned into an F cross DF. That's the calculation at the top of the page. Okay? We're going to do that integral over 6 different triangles, but we're not actually integrating over the whole triangle. We're just integrating over the boundary of this thing. So we're actually integrating over 6 different edges. There's edge ij, then there's the next edge from j to the next vertex, then from that vertex to the next vertex. We're integrating over the boundary of omega, so we're integrating just over these 6 edges around the outside of this picture. So we're summing over all of the edges at the boundary of omega. Right? EIJ stands for edge from I to j of F cross DF. So the way we do that, well, F is constant on edge EIJ. So the way you integrate a constant function over an edge is you just take the average value. Sorry, I apologize. F is linear over that edge. You just linearly interpolate from edge vertex I to vertex j. And the way you get the average value of that linear interpolation is just you take the value at the beginning, the value at the end, and average them. You just add them and divide by 2. So the integral of F just turned into the average of Fi and Fj. Fi is vertex I, Fj is vertex j, and the integral of F over the edge between them is just the average of those 2 vertices. It just ends up being the midpoint of those 2 vertices. So that's why we get Fi plus Fj over 2. And df is just, you got to remember how we integrate a 0 form over a triangulated surface is the integral of the derivative of a 0 form turns into a 1 form, which is just the difference of the value of the 0 form at each point. So we just get Fj minus Fi. And we get another, so that 2 is going to come out of the summation. So we're going to get Fi plus Fj cross Fj minus Fi. Now you got to think about FOIL. That gives you Fi cross Fj minus Fi cross Fi plus Fj cross Fj minus Fj cross Fi. The Fi cross Fj is 0. The Fj cross Fj is 0. The Fi cross Fj and the Fj cross Fi, we can switch the j cross I, turn the negative into a positive, add them. We pick up another factor of 2. So that 1/6 had temporarily turned into a 1/12 because of this 2 here, but then we pick up another 2. When we do all that, I see I've lost every single one of you. I would encourage you to just take this expression and FOIL it out yourself. That's all you got to do. Okay? And then you get this expression over here. All right? All right.
Sorry.
Yeah.
What's Fi cross Fj?
Yeah.
Like, is Fi a vector?
Fi is the vector that points from the origin, wherever that is, to vertex I on our surface.
Cool.
And Fj points from the origin to vertex j. When we cross those, we get the area of that parallelogram. It's a weird parallelogram. It's not a parallelogram on the surface. It goes from the origin, which is inside the surface, to this edge on the surface. Okay, so that's the parallelogram we're talking about. But the trick here, and this is the part you have to really think about, and I'm not going to explain it very well, you could put the origin wherever you want. So going back to this picture here, if I put the origin at vertex P, if that's where the origin, then Fi is just this edge, the edge from P to I. And Fj is just the edge from P to J. And so Fi cross Fj is just going to be the area of the parallelogram that goes from P to J to some vertex out here on the right back to I. So half of that parallelogram is going to be just the area of this triangle. Okay, so that's exactly what's going on. The next slide here is Fi cross Fj just turns out to be the area, half of that turns out to be the area of the triangle from P to I to J. If we add up all those areas, okay, then we're getting exactly this expression. There's one other trick that happened here. You'll notice that in that middle equality, I have absolute value bars around Fi cross Fg because Fi cross Fj is a vector quantity. It's the area times the normal vector, times a vector that points in the perpendicular direction. Okay, so the magnitude of that is the area, Ai Pi sub Pij. The direction of that is the direction of the normal vector. And so we get this red arrow over here, the discretization of n dA around one particular vertex is just the sum of the area of those vertices times ni. Notice I'm going to zoom in on this. The summation here is only happening over the triangles around vertex I. That fancy script n of I, that stands for neighborhood of I. We're only adding up around the triangles around vertex I here. So if you add up the area of all the triangles around vertex I times the normal vectors to all the triangles around vertex I, what we're going to get is some concept of the normal vector at vertex I. And that's one of the things you'll discretize in your homework, your coding homework, is just the sum of, it's called the area weighted vertex normal in the coding assignment. Okay. All right, we're almost out of time, but the next couple of calculations are easier. We've only actually got 4, 5 slides to go through to get through the next couple of calculations, and they're quicker. So we're over the hump. We're over the hard part. Okay. The next calculation, again, from the 2 slides ago, from way back here, we have the df wedge dn is twice the mean curvature times n. Okay, so that's what we're going to use here. The mean curvature times n is df wedge dn. We lost a factor of 2 in here somewhere. I think that's a mistake. There should be a 2 in here somewhere. So modulo some constants that somehow have mysteriously disappeared. The mean curvature times n is df wedge dn. Okay. Since it's a vector valued quantity, we can switch the wedge product. Wedge product is commutative on vector valued quantities. It's anti-commutative on real valued quantities, something we talked about before break. Here we're going to just rewrite this as the derivative of n wedge df. That allows us to use the generalized Stokes theorem and replace the integral over C with the integral over the boundary of C. Okay, now C here is, again, this dual cell that's pictured in this picture on the right. So when we're integrating over that dual cell, it becomes a summation over the boundary of the dual cell. But the boundary of the dual cell are these little dual edges. So like this edge from A to B, that's one element of the boundary of this dual cell. Okay. So we're integrating n wedge df. And remember, the definition of n wedge df is it's the 2 cross products. N cross, well, actually what's going on here is the integral over n wedge df over eij star. So eij star, that's the edge going from A to B. We're gonna break that up into 2 integrals. One from A to M and one from M to B. Okay, this is a little bit hard to get your head around, so I made another slide. The integral from AM to A is just NA cross M minus A. The integral from M to B is NB cross M minus B. But when we take the normal vector to this picture, which you can't see, it's pointing straight at you, and we cross that with M minus A, well, if I take the cross product of a vector coming straight toward you with a vector pointing to your left, I just get a vector pointing straight up. Okay, so if I cross M minus A with NA, I get a vector that points from M to J, sorry, points straight down. And similarly, if I take the cross product of M minus B with a vector going straight toward you, now I get a vector that points straight up. So I get these, what I get is something, when I add those two back, I get something that points in the same direction as EIJ, but it has length equal to the length of the dual one cell, which is in the perpendicular direction. So the relation between the length of EIJ and the relation between and the length of the dual edge we'd seen before, that's just given by the cotan formula. So that mysterious cotan formula is popping up again. That's just the relation between the dual edge length and the original, the primal edge length. That's why that's coming up there. There's a lot to digest there, I know, and I'm talking very quickly because I got 2 more slides to get through. But this is understandable if you take the time to just read through. I think the hardest part is actually going from N wedge DF to the 2 cross products. Going from those 2 cross products to the cotan formula is just recognizing that that's the cotan formula is the relationship between the dual edge length and the primal edge length. Okay.
So N sub A and N sub B are like triangle normals?
Those are triangle normals. Yes, that's the normal vector to triangle, the triangle. This little white dot here is representing a vector pointing straight at you. That little white dot is supposed to be representing N sub A. When I take N sub A and I cross it with M minus A, I get a vector perpendicular to M minus A, which will point in this direction straight down here.
Okay.
All right, so the most complicated formula on this whole page is that center one, and that's where that's coming from. And again, this is being defined only in the neighborhood of a single vertex. This is just letting us discretize the mean curvature times n around a single vertex. Last one to get through. Now this is the shortest one for sure. It's a very similar calculation to what we just did. Kn is just dn wedge dn. Again, that's from those normal vector calculations we did a while ago. Dn wedge dn we can rewrite as the derivative of this form. Now we can use the generalized Stokes theorem to get rid of the derivative and rewrite it as an integral over a boundary. Okay, same thing we were doing before. Now we can look at the wedge product and rewrite it as a cross product because that's how we've defined wedge products for vector valued forms. Okay, there's a little bit to think about here. What the hell do we mean by the integral over the edge? And he makes a note here up top. He says rather than, stop that. No, I don't want to do this. He says rather than viewing this as an integral over a line segment in R3, it's easier for calculation purposes to integrate over the puffed out version. So remember when we were doing Gaussian curvature, we took these flat triangles and we puffed them out onto a sphere. So rather than integrating them on the piecewise flat thing where all the triangles are flat, we're going to do these integrals over this round thing on the sphere. And when you do it over the round thing on the sphere, I'm not going to go through this because it would take a while to explain, but these calculations end up simplifying quite a bit. And what you end up with is just an expression that involves the length of each edge, the edge vector itself, and the dihedral angle, the angle between 2 adjacent faces. So this is exactly where this last formula is coming from down here is, see if I can zoom in here. curvature vector, Gaussian curvature times the normal just around a single vertex is going to be the sum of the angles at the edges between the faces. Those are the Phi-ij's. It's the edge between one face and the next face, times the length of ij, that's the length of that edge ij, times eij, which is just the edge from vertex I to vertex j. That's this fi minus fj. That's another way of saying eij. Okay, that's a lot to digest. I know that's a lot to digest. There's a lot here. This is one kind of summary of those last couple of slides, just what you should take away from all of that, those last few slides. And a lot of these expressions are recreated, they're reprinted for you in the coding assignment. In the coding assignment, again, all you're doing is just implementing these formulas. You're just literally typing these formulas in and hoping the program will do it itself. Okay. There's a whole different way to view every one of these discretizations, which is by using something called the Steiner polynomial. That's what we're going to do next time. So next time we're going to forget about everything we did today, and we're going to do all these arrows on the right side of the picture. And if you'll notice, we missed one arrow on the left side, which is this one, the integral of the mean curvature. And we'll be able to pick that up actually next time when we do Steiner polynomial. Somehow that one pops up as well. So it gives you a nice overview. If you look at, there's these gaps in this picture. Right over here, there's this gap between NDA and the integral of NDA, and this sum and this sum. And the Steiner polynomial allows you to kind of link this whole square of things in this flowchart to this next square of things in this flowchart. We've got this Steiner polynomial here that links those two squares, right? So you end up with this nice picture of how everything is related to everything else. That was a whole lot. We are out of time. I see we're 5 minutes over time. So I encourage you to go back, look at this slideshow yourself at your own pace. If there's anything you want explained, you can feel free to pop into my office hours tomorrow. Pop into Catherine's office hours where you watch this video. Email us questions. Use Piazza to post questions. You've got a lot of resources.
Breeden, will you have office hours in an hour? Okay.
Also, the coding assignment is due in 2 days, but it's not posted on Gradescope yet. Is that going to go up soon?
Yeah, I can do that this afternoon.
Cool.
But feel free to just email it to me too if you want. I can upload it for you when I get that done.
Thanks.
Other questions? Catherine, anything you want to add?
Nope.
Okay. All right, so I will see you all either in my office hours tomorrow or next Thursday. Cool. I think next Thursday is not going to be nearly as brutal. So all right. See you guys.
UIO Pringles.
Right.